Hey, 42 here. The history of the computer goes back further than most people think. The very first automatic mechanical computing device, for example, was built in 1822 by English polymath Charles Babbage. Admittedly, the difference engine, as it was known, was pretty basic by today's standards. It was powered by a hand crank for a start. But Babbage's device was capable of automatically computing values for polynomial functions. By 1837, Mr. Babbage had drawn up plans for an even more advanced kind of machine, the analytical engine. As it happened, this was to be the first ever design for a general-purpose programmable computer. And when Ada Lovelace, the only legitimate child of one of the greatest English poets in history, and full-time rake, Lord Byron, wrote an algorithm for this theoretical machine, she became the first computer programmer in history. Sadly, and despite Mr. Babbage working on this device on and off until he died in 1871, it was never completed. But the design was so groundbreaking that Babbage is known today as the father of the computer. And what a proud father he would be if he were still alive today. He definitely isn't, by the way. You can go see half of his pickled brain in the Science Museum in London. Since his death, Babbage's metaphorical electronic offspring have changed the world beyond all recognition. Despite the famous prediction of one-time IBM CEO Tom Watson, who in 1943 estimated the total global market for computers would stretch to around 5, yes, he meant a global demand for 5 individual computers, there are now thought to be more than 2 billion of the things in homes and offices around the world. If Charles Babbage truly is the father of the computer, he has spread his seed far and wide. Of course, the kinds of computers we're familiar with today are of the digital variety, and these arrived on the scene in the 1930s, around 100 years after Babbage's mechanical difference engine was built. In the 90 years since, the leaps forward that have been made in computing are frankly astonishing. As you may have already heard, the Apollo 11 spacecraft that brought Neil Armstrong and his fellow astronauts to the moon in 1969 was about as powerful as a modern calculator. 50 years later, a common piece of tech that most of us use daily to stay in touch with our friends and generally piss about, the smartphone, is quite literally millions of times as powerful. These exponential increases in computing power we've witnessed are broadly described by Moore's Law, named after Intel co-founder and one-time CEO Gordon Moore, which states that the processing power of computers doubles roughly every 2 years. But the biggest driver of Moore's Law has been our ability to shrink the physical size of key components in our computer processors, particularly transistors, year on year. The smaller you can make your transistors, the more you can squeeze onto your chip, and the more computing power you have at your disposal, measured by computer scientists as flops, or floating point operations per second. The problem is, the smallest transistors today are just a few atoms across. Pretty soon, smaller just isn't going to be an option. Manufacturers are coming up with clever new ways to keep processor power rising, but it's becoming increasingly expensive and challenging to do so, which is why, for the first time in 50 years or so, Moore's Law no longer applies. Exponential gains in processing power are becoming a thing of the past. This doesn't necessarily mean we're reaching peak computer, but it does mean that we're no longer making the kinds of huge strides forward that have powered many of the technological and scientific advances humanity has achieved in recent decades. Now, you might be sitting there thinking to yourself whether we actually need more computing power. After all, if we could fly to the moon on a glorified pocket calculator, the most powerful computers of today should be able to do pretty much anything, right? So long as we have enough of them. Actually, not so much. The most powerful supercomputer in the world today is IBM's Summit. It's the size of around 2 basketball courts and uses 136 miles of cables. It's capable of executing a quintillion operations per second, a number that sounds like it was made up by a 5-year-old to win an argument. And it's being used to push back the boundaries of human understanding in fields like energy, AI, and healthcare. All very impressive sounding, but there are things even Summit can't help us with, at least not unless we have a spare few million years to leave it running. Certain mathematical problems are just extremely resilient to solving by classical computers, even really big shiny ones like Summit. The most commonly wheeled out example is prime factorization, finding 2 prime factors of a given number. Make that given number large enough, and classical computers simply aren't up to the task. Now, factoring large numbers might seem like a fairly arbitrary thing to want to do with the world's most powerful computer. I mean, I'd just like to know, can it run Crysis? But it just so happens that the fact it is very, very hard to solve these problems with any kind of regular computer is one of the foundational principles of internet security. But you can make sure you're already 2 steps ahead of the game by vastly improving your personal security with Dashlane, who have kindly sponsored today's video. The best way to protect yourself against hackers, spammers, and other online threats is by using the leading password manager and all-in-one security suite, Dashlane, who will store all of your passwords in a super safe way without ever having access to them or allowing anyone but you to view them. Dashlane creates strong and unique passwords for all of your online accounts and autofills them, so you never have to click forgot password ever again. And you don't have to sweat about the extremely rare chance that Dashlane could be breached, because Dashlane safely stores and decrypts your data on your local device only using your master password. This means that Dashlane never has access to your personal data, and any hacker would only see random noise. Dashlane also autofills your credit card information whilst online shopping, so you can make purchases without having to fetch your wallet. Dashlane has a built-in VPN to encrypt your data and keep your online activity anonymous. Best of all, it works on any device. Whether you're protecting your top secret blueprints to quantum supremacy or videos of your cat, there is no better way to make your online world impenetrable than by using Dashlane. From my experience, Dashlane is the best all bases covered security and time-saving tool out there. You can try Dashlane for free on your first device by heading to www.dashlane.com/42. Then if you decide you want to upgrade to premium, use my code 42 for 10% off. So, if our ability to make more powerful classical computers is diminishing, and there are still problems out there that we don't have the tools to solve with current technology, do we just have to accept that we're reaching the limits of what we're capable of as a species? Actually, no. We just need to build a different kind of computer, one that transcends the natural physical limits of microchips. A quantum one. The first thing we should clear up is that quantum computers are not simply a newer, faster version of regular computers. That means if all you want to do is watch YouTube and share memes, you're better off hanging on to your trusty laptop, even if a few of the keys are beginning to stick. Quantum computers work in a drastically different way to regular computers, and they're good at doing different things. Just how a light bulb isn't a better version of a candle. It's a different way of generating light. A quantum computer isn't a better version of a computer. It's a completely new way of approaching computation. Let's start with the basics. The fundamental unit of information in a classical computer is the binary digit, known as a bit. These bits have 2 possible states, either 0 or 1. And strings of them can be used to encode information. You can think of them as a series of very simple switches. It might not sound like much, but at a fundamental level, bits underpin pretty much every single thing you do on your computer. Yes, even that. A quantum computer, on the other hand, has qubits, literally quantum bits, instead of regular bits. Just like regular bits, qubits have 2 possible basic states, either 0 or 1. But unlike regular bits, qubits are, for want of a better way of putting it, pretty f***ing weird. In our classical computers, the state of a bit is fixed at any given time. It's either 0 or 1. And sure enough, qubits have a 0 and 1 state also, represented by how they are aligned within their host magnetic field. In quantum mechanics, this is called spin. And the two possible states are spin up and spin down. But there is a magical third state. Well, it's actually not a state at all. It is, to put it in lay language, a combination of both known states. You see, whilst a quantum computer is operating, the state of each qubit is undefined. There is some probability of each qubit being a 1 and some probability of it being a 0. This undefined state is known as a quantum superposition, where it can be considered to be in both spin up and spin down at the same time. And only when we observe the system will a superposition collapse and the qubit will settle on one of its two basic states. It's an odd concept, but many of you will have come across it before in famous feline torturer Erwin Schrödinger's thought experiment, known as Schrödinger's cat. Before we open the box, the cat is neither alive nor dead, but is in a superposition of the two. Only when we open the box and observe the cat is it one or the other. Explaining exactly how quantum superposition makes quantum computers so powerful would take several textbooks, a boatload of maths, a theoretical physics education that I don't possess, and an exploration of some other weird quantum phenomena like quantum entanglement or spooky action at a distance, as Einstein called it. But the general concept is this: a classical computer can only be in one basic state at a time. That means when trying to solve a problem like prime factoring, where there are many potential solutions to sort through, broadly speaking, it must check each solution one after the other. But when a qubit is in a superposition, it's able to process huge numbers of classical states in parallel, which allows it to do certain kinds of calculations exponentially faster than a classical computer could. Eric Ladzinski, co-founder of quantum computing company D-Wave, explains it like this. Imagine that you only have 5 minutes to find an X written on the page of a single book amongst 50 million other books in the Library of Congress. If you search for the X like a regular computer, one page at a time, you would never find it before your 5 minutes were up. But if you had 50 million parallel realities, and you could look at a different book in each of those realities, you would find the X much, much faster. In this second example, a quantum computer splits you into 50 million versions of yourself to make the work quick and easy. And you may think, but we've had parallel computing for over 50 years. One of the big two retail microprocessor manufacturers, AMD, sells a CPU that has 64 cores, and you can slot it right into your home desktop computer with the right motherboard. And NVIDIA's latest GPU can compute almost 5,000 problems in parallel. Why don't we just keep improving these existing technologies? Well, because of the atomic level physical size limits of transistors that we touched on earlier, we're quickly nearing the limit of how much further we can push this parallelism. Unless we change the rules of the game, we'll never reach the aforementioned 50 million parallel processors of a quantum computer using classical computing hardware. Because adding more cores to a classical computer system increases its power linearly, providing the software can take full advantage of each core, of course. Conversely, with quantum computers, with each qubit you add to the system, the amount of parallel processes you can run increases exponentially. So with 2 qubits, you can consider 4 potential outcomes at once. But with 4 qubits, you can consider 16. And if you were to pack just 300 qubits into a quantum computer, it could consider more variables at once than there are particles in the known universe. Now that's what I call parallel computing. Now, it's possible that you might be feeling a tad confused right about now. If so, that's awesome, you're probably getting it. After all, Richard Feynman, the man who originated the idea of the quantum computer in the first place, once said, "If you think you understand quantum mechanics, you don't understand quantum mechanics. Seeing as he went on to win the Nobel Prize for his work in quantum mechanics, it's a safe bet he knew what he was talking about when he claimed he didn't know what he was talking about. Okay, so all of this sounds great, but what can we actually use quantum computers for? Earlier on, I mentioned that quantum computers are much, much better than classical computers at finding the prime factors of very large numbers, which is a foundational principle in data encryption and digital security. It's been estimated that a classical computer would take trillions of years to crack RSA's 2048 encryption, which is commonly used to secure data transmission online. A quantum computer, on the other hand, could do so in a matter of hours, effectively rendering modern online security obsolete. But before you withdraw all your money from the bank and start shoveling it under your mattress, don't worry. Digital security has always been an arms race, and in this case, the good guys have a pretty big head start on the bad. Post-quantum encryption methods are already being developed that will be able to thwart even quantum computers, though admittedly, implementing them will still require a radical redesign of the way encryption works online. Think something along the lines of fixing the Millennium Bug, a mythical insect that, if you're any younger than I am, you've probably never heard of, but don't worry, it turned out to be rather harmless in the end. Beyond internet security, there are many theoretical applications for quantum computing. Plans are already in place to use quantum computers to create wildly powerful AIs by supercharging the machine learning process with quantum algorithms. The downside, of course, is that these AIs will one day rise up and destroy us. But in the last few seconds, before we're finally exterminated, we'll all be able to take great pride in how clever we were to come up with quantum computers in the first place. Quantum computers are also, unsurprisingly, extremely good at simulating quantum physics itself. This was in fact the original application Feynman had in mind when he came up with the concept, since the complexities involved make this an area unsuited to classical computers. Classical computers are so inaccurate when it comes to physics that all existing models broadly approximate the, in vastly simplified terms, rules of the universe, which isn't tremendously useful to scientists. But with quantum computers able to model immensely complex interactions at the particle level, we will be able to make huge advances in designing new drugs, materials, solar cells, high-temperature superconductors, as well as many other niche but incredibly impactful use cases, such as modeling chemical catalysts for use in making better fertilizers. Quantum computers will also help us perfect the optimization of complex systems like traffic flow and logistics problems on a massive scale. We'll be able to accurately model national and global financial systems with currently impossible levels of granularity and complexity, which could either be used to highlight financial weak points and level up society, or predict what the markets will do next and make the banks even richer. Only time will tell, but I'm betting on the latter. Okay, so quantum computers are going to be awesome. We seem to know exactly what they're going to look like and how they would work, so why haven't we just made one already? Well, it turns out they're actually pretty tricky to put together. Qubits themselves are typically made from subatomic particles like photons or electrons. Firstly, you have to isolate them, and to get them to reliably perform the weird shit we talked about earlier, you need to make them very, very cold. And we aren't talking, oh, it's a bit chilly in here, maybe I'll put a jumper on cold. We're talking literally colder than the nut-shriveling darkest reaches of outer space cold. In fact, it's a balmy 2.7 Kelvin. Outer space looks like a tropical holiday compared to what's required to run a quantum computer. Just 0.015 Kelvin. That's about minus 273 degrees Celsius to those of you who don't speak science. Or to put it another way, almost as cold as it is physically possible to make something in our universe. That being 0 Kelvin or absolute zero. Even at this temperature, qubits are very unstable and prone to decoherence, which occurs when the surrounding environment interacts with them and errors are introduced to the system. All things considered, attempting to make a quantum computer presents a vast engineering challenge and requires monumental amounts of cash, which is why the good guys will have a huge head start in developing new quantum security protocols. It could be a further decade or more before this monumentally challenging technology trickles down to your everyday basement hacker. And it just so happens that there is one entity out there with some pretty nifty engineers and very deep pockets who actually have made a working quantum computer already. Just last year, Google claimed to have achieved something called quantum supremacy with their 54-qubit quantum computer called Sycamore. Quantum supremacy is not, as it sounds, racism against regular computers, but is defined as a quantum computer completing a computation that no classical computer could match in a reasonable amount of time. Google claims Sycamore ran a random sampling calculation in 200 seconds, something they say would take the most powerful classical computers available today around 10,000 years. Admittedly, IBM did come along the very next day to piss on the quantum barbecue by claiming their supercomputer Summit could complete that task in 2.5 days. But that is still significantly longer than Sycamore took, about 1,000 times longer in fact, and all with just 54 qubits. So why didn't you hear about this literal quantum leap forward for humanity? That's a good question. But then, many of the most influential inventions in history have been underappreciated to begin with. Today, there are tens of billions of light bulbs in use around the world, but when Thomas Edison and his team invented this new and improved version of the candle, that wasn't a candle, leading scientist Henry Morton of the Stevens Institute of Technology predicted it would be a conspicuous failure, and the British government felt it was unworthy of the attention of practical or scientific men. Quantum computers are still very much in their infancy, but they are absolutely already here. And though the full implications likely won't be understood for some time to come, one thing's for sure, they will most definitely change the world. Thank you for watching. Thanks for watching, and thanks again to Dashlane. Don't forget to check them out using the link below.